Welcome to Maths with EJD. In this video, we're talking about separable ordinary differential equations. In the last video, we started talking about, we saw generally first order ordinary differential equations, and we saw things like solution, general solution, and particular solution. So from this video onwards, we'll be looking at different methods for solving first order ordinary differential equations, depending on what they look like. Okay, so for an overview, a separable ordinary differential equation. Okay, let me just write it in full for starters, and I can always write ODE later. A separable ordinary differential equation ODE is one in which the variables, that's the dependent and independent variables, can be separated on either side, on either side of the equation, allowing us to integrate each side independently. So we can separate, if you're dealing with y as a function of x, right? So we can separate all the y's together and all the x's together and integrate to get our solution. Okay, so after then, we can talk about what we can call the separable form. Separable form. What does it look like generally? Separable form. Okay, so a first order. So, I mean, in this series, we are talking about first order differential equations for the most part, starting from the last video. So, a first order differential equation, a first order, a first order ordinary differential equation ODE is said to be separable if it can be written in the form dy dx equals g of x, h of y. So that way, you can put dy and h of y together, and then you can put the x and g of x together, right? So this is the separable form in generality. So where g of x is a function, g of x is a function of the independent variable, a function of the independent variable x, okay? And h of y is a function of the dependent variable y. Okay, so we can separate them like that. Now, what is the goal here? The goal, the goal is to separate the variables x and y so that all terms involving y are on one side and all terms involving x are on the other side, are on the other side. Okay, so with that done, let's talk about method of separation of variables. Method of separation of variables. Okay. So how do we apply this method? So to solve to solve a separable differential differential equation, follow these steps. So the first thing is you rewrite the equation. So what this simply means is that, okay, rewrite the equation, right? To separate, to separate, separate variables x and y. Okay, so you rewrite the equation to separate variables x and y. Okay, this will involve algebraic manipulation to isolate the y dx on one side and the x terms on the other side. Okay, so that's the first thing you do. The second thing is to integrate both sides. Integrate both sides. So now that you've separated, you can integrate both sides since they have the same variable. So after separation, you integrate both sides with respect to their respective variables. And the third thing to do is to solve. So after integrating, you solve for y of x. You know, like I said, when you solve a differential equation, you are looking for you're actually looking for y of x, you know, or you're looking for the variable the an expression which is the independent variable with respect to the independent variable. So solve for x if possible. So it is not in all cases that you can solve for x because some of these results may be implicit. So solve for x, for y of x if possible, to obtain explicit solution. So if it is possible, you can solve to obtain explicit solution. If not, you leave it in the implicit form. Okay. You may need to apply initial conditions to determine any constants of integration. So if you have initial condition, you apply so you can get some constants of integration that may be necessary. Okay. So let's take an example now. Example. So imagine that you need to solve dy dx equals 2x over y. Now, if you look at this, this would be like you have, let me do it this way. So imagine this is like you have dy dx equals 2x times 1 over y. So this is now like your following the general pattern that we showed the other time. So this is like your g of x, 2x is like your g of x, while 1 over y is like your h of y. So it's a very perfect example of the separable equation. Okay, so since we have to solve this now, can we then go ahead and say this? Take step one, like we've just been told, step one. You separate the variables, the variables, separate the variables. So you have dy dx equals 2x over y in variable separable form, like I said the other time, right? Okay, well, I mean, I've shown that it is variable separable. So you cannot collect the variables together, similar variables. So here you have this is dy and y, and this is dx and 2x. So from the look of things, we can just cross multiply, like we say. So cross multiply, and then you have y dy equals 2x dx. This is one of the simplest ways that you can have. So that is step one already. So you have separated all the y's together and then all the x's together. Okay. Then we move on to the second step where we now integrate. So step two, integrate both sides. Integrate both sides. And to integrate both sides, you have integral of y dy equals integral of 2x dx. So if we go on with this, it means we have integral of y dy equals 2 integral of x dx, just to, that's just a nice step to take. So if you integrate y with respect to dy, you get y squared divided by 2, and this is equal to 2 into, if you differentiate x with respect to x, you get x squared divided by 2. of course, we always have to add an arbitrary constant c. Okay. So we say, okay, I mean, c is the arbitrary constant. I'm going to make that statement later. So here now you have, of course, 2 cancels 2 here. So we have half y squared equals x squared plus c. Okay. So then we can say where c is the constant of integration, is the constant of integration, or what you can call the arbitrary constant. Um, under differentiation and integration, I explained why we have that. So you can visit the basic calculus playlist to get that gist. Okay. So now step three. So step three is to solve for y of x, solve for y of x. That's what's up next. So from what we have up here, right? Okay, we are looking for y. So we have half y squared equals x squared plus c, x squared plus c. So since we're looking for this y now, so y has fraction half beside it and it has power on top of it. So the first thing we can do is to multiply through by 2 to remove the fraction. Okay, and afterwards we can think of maybe taking square roots to remove the power. Okay, like that. So we can multiply both sides by 2, right? So we have 2 times half y squared equals 2 into x squared plus c. Okay, so 2 cancels 2 here. So we have y squared equals 2x squared plus 2c. Of course, 2 is a constant multiplied by c. That is still a constant too. And then we have y alone with power, so we can take square root of both sides. So what we have done here is multiply through by 2. And the reason is to remove the fraction. And then the next thing is the power. So to remove the power 2, we have to take square roots. Okay. So we can say take the square root, take the square root of both sides. Take the square root of both sides. And what do we get? We have y squared square root, right, equals square root of course, plus or minus, right? 2x squared plus 2c. So power 2 cancels the root. So you have y is equal to plus or minus square root of 2x squared plus 2c. All right. So now this is general solution because it still contains an arbitrary constant. So this is general solution like we looked at in the last video. This is general solution. Okay. Now let's look at a kind of application. Sometimes when you separate the variables, you may have to you may have to resolve them into partial fractions and all that. So probably you're going to have, I'm going to give you an example in that involves something like that. But let me do a kind of practical application example right now to see. So these are the top here. You can consider it as example 1, right? Example 1. So let's take another one, which is our example 2. So let's imagine that we have example 2, and that example 2 is this. We want to like an application. So application to, so if you had an initial condition here, we could just get the value of c and then we can continue, but we don't have initial condition, so we just stop here. So that's our general solution, and without initial condition, that's where we stop. Okay, so application to an exponential growth model. Okay, so imagine you have dy dx, I mean dy dt now equals ky. So since you're talking about growth model, so time is involved, right? So where k is constant, okay? In that case, we now want to say we want to solve for, so solve dy dt equals ky. So where k is constant. So step 1 again is just say you have dy dt equals ky. So there's no x here, but at least we can see y is separate on its own. So we can separate the variables, right? So separate the variables like we've always done. So y can go with dy. So and the only way to do that is to divide both sides by y and multiply both sides by dt. Okay. So here we have 1 over y dy. Okay. Um, I'm trying to look for a neat way to say that. Okay. Basically, let y come here and let dt come here. Basically, that's all I'm saying. So it means that we have dy over y equals k dt. Basically, that's all I meant to say. So with that in place now, so we can now integrate both sides. Integrate, now that you've separated the variables, integrate both sides like we've always done. That's the second step. So we have integral of dy over y equals integral of k dt. Okay, so that's like integral of 1 over y dy equals k integral of dt. Okay, because k is constant. So, and from our law of calculus, when you integrate 1 over y, you're definitely going to get ln y. So you're going to get ln absolute value of y, because if y is negative, right, you won't be able to get this. You won't be able to, it will be undefined. So you get ln y equals k. When you differentiate the t with respect to t, you get t, and then you can have an arbitrary constant as usual. So the next thing is to solve, of course, where c is the constant of integration as usual, constant of integration. So the next thing is to solve for y of t. Solve for, you now know y of t. So t is the independent variable. This time is the independent variable, yes. So you have ln y equals kt plus c. Okay, so we are looking for this y now. So y has ln disturbing it, and it also has absolute value disturbing it. So what do we do? So the way to remove ln, ln is is log, right? So the inverse of log is exponent. So you can now exponentiate. You can exponentiate both sides, to eliminate the logarithm, eliminate the logarithm. Okay. So it means you have e raised power ln absolute value of y equals e raised power kt, e raised power kt plus c. Okay. So since we are looking for y, right? So it means, and whenever you have e raised power ln, so that's a way of neutralizing. So you have absolute value of y left, and this is equal to e raised power kt. From the law of indices, this is more like e raised power kt times e raised power c. Okay. So if you now say let e raised power c be equal to c1, all right? So where c1 will now be a new constant, because e raised power c is constant, so e raised power c is another constant entirely. So where c1 is a new constant, c1 is now a new constant. Okay. So if you do that, we now have from here now, we now have y of t. So the absolute value can rest. So we have y of t equals, so because this one is c1 now, so we have c1 e raised power kt, c1 e raised power kt. And this is our solution. So this is the solution to the exponential growth equation. Of course, as it is now, this is a general solution because we don't have initial conditions. So it is a family of solutions, like I said in the last video. It is a family of solutions. So let's try to visualize that solution using Desmos. Let's see what it looks like. It's a family of solutions. So depending on the value of C1 and all that, we can get, so let me just call it C in this case, right? So we have C, then E raised to power c e raised to power kt. Okay, so uh, um okay, in this case, right, because the response recognizes just y and x, so it's better we say e raised to power kx. So it sees x as a variable. So c, the value of c can now vary. So we can do a slider for c and we can do a slider for k. So imagine if k is 1 and c is 1, this is what you have. Okay, so imagine if you now if we slide k to the negative, see what we have. If we slide it to the positive, this is what we have. So if we keep this one at 1, say we keep this one at 1, struggling to keep it at 1. Okay, good. So, and then imagine you slide the C also. So it also switches it over. But I mean, to visualize it better, so let's pick values. Let's pick values. Let me say, let's pick uh different values, right? For C and K. I'll just pick the values randomly so we see what happens. So let's assume that when C is 1, right? You've seen that already. So let's just imagine that we have, okay, let's start from like -3, that is our C. Then E raised to power, let's now say K is also -3. So I'll just go like that, X. So see what you have. So because that's like, it means that C1 is -3 and K is also -3. So I just want to go like that. So what if you come here and then C1 is -2 and K is also -2? See what you get there. And then when you come here, you have C1 is -1 and K is also, okay, I don't even have to put 1. So just say minus. So see what you get. And then we can now come and have, of course, C1 cannot be 0. If it is 0, then the solution is gone. I mean, it can be 0 for sure. And that means that'll be 0, right? So can we just do okay, let's just switch over to 1. So we have this now, and this is just E raised to power X. So it's, you can see it at that one becomes positive, it switches over like that. And we can have 2E raised to power 2x. See what that gives. And then we come again to 3. So we have 3e raised to power 3x. So that also goes. But we can also do some kind of switching. What if we have -3? So let's pick C1 is -3. So we have -3 e raised to power k is now, maybe k is now 3, and then we have x. So you can see that throws a new dimension into the whole situation, as you can see. So we have negative C1 but positive. So all these are possible solutions to the same problem, right? Because that equation y of t equals C1 e raised to power kx can take any of these forms. So that's why we say it's a family of solutions. So imagine you now have -2e raised to power 2x. So see what you get there. That new line is added. What if we now have minus e raised to power x, raised by 1x. So it throws in that blue thing into it. So you have this whole family of solutions, and they are all possible solutions to the same problem. Okay. So that's what we have in this case. But I mean, because it's a general solution, so you have a family of solutions. But if you have an initial condition or a boundary condition, then you can have a specific result, which is called a particular solution. Okay. Now, with that, uh taken care of now, can we talk about some applications? Applications. I mean, we have seen an application already. Or better still, I think let me just leave this alone because we are going to have a whole video to talk about applications of first order differential equations. So all this will still come up. So let me not bother. Let me just go straight to practice questions. Practice, let me just call it practice, right? Practice. So I'll drop a couple of questions for you to try your hands on. So can you try to solve? This is one. I'll solve dy dx equals 3y over 2x. So you can separate and solve, right? Then number 2, solve the following differential equation. Okay, let me just say solve. dy dt equals, or better still, dy dx equals 5y cos x. So 5y will go with y, cos x will go with the x. Okay. Number three, can you also the kind of thing we've done now, it's a growth and decay model. So solve the following differential equation that models population growth. So again, solve dy dt equals 4y. So now it's more like we have our k to be 4 from the last example we did. Then number four, we can also talk about radioactive decay. So just like we said, right, this is actually for growth model. Okay. So here you can also solve. So when this coefficient is positive, that's a growth model. But when it is negative, it is a decay model. So solve dy dt equals -1/2y. Because of this negative sign, now this becomes a decay model. So it means that the value of y will be decaying, it will be decreasing. Okay, that's what that is about. Okay. Um, so you can also talk about a logistic model where you have like this kind of situation, number five, like this situation where you have dy dt, you want to solve dy dx rather equals y into 10 minus y. This will require resolving into partial fractions. So if you don't know partial fractions already, you can actually see my videos on integration by partial fraction. So I actually took time to break down the concept of partial fraction there. So this kind of equation is actually called the logistic model. It's the logistic model. So the model actually saturates at some point. It doesn't just grow exponentially like what we just saw. So you could actually have you know, number six. Number six, you can also uh, deal with a cooling problem where you solve the T. So that's the rate of change of temperature with respect to time. And that is equal to minus 0.1. So it's minus tells you that the temperature is decreasing into T minus 20. So this is actually a cooling problem. This is a cooling problem. So negative tells you it's cooling, right? It's a cooling problem. If it is positive, if this sign was positive, that will be a heating problem. Okay. So that actually also is possible. And this is also going to involve separation, resolving into partial fractions, okay, before you can integrate. Okay. Uh, um, okay. Then you can also have number seven. Inverse proportionality is possible to where you need to solve dy dx equals 10 over x squared. Okay. So that will also, so this involves inverse proportionality. Inverse proportionality. Okay. Now for this practice, right, I feel like taking care of one of the problems, right? Let's take this logistic model and see how we can deal with that. So just for an example, so let's take that's question four, right? Question, that logistic model question, that is question five. So question five. So I will not waste too much time on this since you already know the process. So dy dx is y into 10 minus y. So this is only y, right? So automatically we are going to have dy all over y minus all over y into 10 minus y, and that will be equal to dx. Okay, that's how we separate this. So the next thing is to integrate. But I mean, before we can integrate, it doesn't look like normally we should be integrating this, right? But this side is not looking like something we can easily integrate directly. So what we're going to do is, it's the same thing as integral of 1 over y into 10 minus y dy equals dx. And the right hand side can easily be integrated. So we have to take care of the left hand side since it's a compound fraction. So we have 1 into y minus 10 minus y. So we have to resolve into partial fractions where we say a over y plus b over 10 minus y because both are linear. So if you multiply through by the LCM, which is y into 10 minus y, we have 1 equals a into 10 minus y plus b into y. Okay. So if we multiply through by the LCM, so we can then use cover up method. Okay. We can use cover up method and we say if y is equal to 0, if y is 0, this by automatically goes out and we have 1 equals 10a, and that implies that a is equal to 1 over 10. Okay, so we have the value of a like that. Then on the other hand, if y is equal to 10, the reason why we are setting y to be 10 is that if y is 10 here, so 10 minus 10 can go to 0. So a can cancel that. That's the idea of cover up. So we have 1 now equals by will now be 10y again. And that, oh, sorry, by, since y is 10 on that side, so we have 10b. So b again is going to be, this is going to imply that b is also 1 over 10. So we have 1 over 10 for each of them. So we can now go back to this expression and deal with it. So we can now come back here, okay, and say we have integral of 1 over, okay, no, it's a 1 over 10 over y plus b into, b is also 1 over 10. So, okay, I guess instead of jumping, let me just take my time, okay? So we can say, therefore, 1 over y into 10 minus y, which is the same as a over y plus b over 10 minus y, will simply be 1 over 10y plus 1 over 10 into 10 minus y, okay? That's what we have for that. So we can now integrate. So we can also integrate. So therefore, integral of 1 over 10y plus 1 over 10 into 10 minus y, okay? This is the whole, this is this expression now, okay? All of this with respect to dy is equal to integral of dx. So this looks easier to integrate, right? Because you're going to have integral of 1 over 10. Okay, we can take 1 over 10 out, in fact. So we have 1 over 10 integral of 1 over y dy plus 1 over 10 again, integral of 1 over 10 minus y dy, okay? And that is equal to integral of dx. So when we integrate 1 over 10 minus y, this is, if you differentiate y, you get 1, right? If you integrate 10 minus, if you integrate 10 minus y, you get minus, if you differentiate y, you get 1. And that's why the answer is going to be ln y. But here, if you differentiate 10 minus y, you get minus 1. But what you have at the top here is 1. So you have to find a way. So here, of course, this is just 1 over 10 ln y straight. But when you come here, you have to be a bit more careful. So this is integral of, so you need minus y here to be able to say this one is ln something. So this has to be minus 1 times minus 1. Minus 1 times minus 1 is 1, all over 10 minus y dy, okay? Of course, if you integrate x, you get x plus constant c. So here now, you're going to have 1 over 10 ln absolute value of y, okay? Then you can bring out one of the minuses, so that's minus 1 over 10, okay? Integral of minus 1 over 10 minus y. Now, if you differentiate 10 minus y, you get minus 1, and that's perfect. So we can say that is actually ln 10 minus y. Now, so this is 1 over 10 ln y, okay, minus 1 over 10 ln absolute value of 10 minus y, okay? That is equal to x plus c. So at this point, we can now begin to talk about solving for, we can begin to talk about solving for y. So the first thing we want to do here is multiply through by 10, right? So we can just have ln y, okay, minus ln 10 minus y equals 10x plus c, okay? So we can then solve for y. So to solve for y here, we have, so this ln means we can simply have ln absolute value of y all over absolute value of 10 minus y. That's from the law of logarithm. That is equal to 10x plus 10c, okay? So again, we can exponentiate. So we have e ln absolute value of y, okay? Absolute value of over absolute value of 10 minus y, and that is equal to e raised to 10x plus 10c. So that way, this can cancel out. So we just have y over 10 minus y equals e raised to 10x equals e raised to 10x plus, oh, this is 10c, right? 10x plus 10c. So then, I mean, this whole thing again, we have to deal with it. So this is y over 10 minus y equals e raised to 10x times e raised to 10c. So if we call this one c1 like we did before, so this is going to be y all over 10 minus y equals e raised to 10x. In fact, if we call this one c1, right? I've already said we should call it c1. So this is c1. So we have c1 e raised to 10x. So with this now we can solve for y. So we have y equals c1 e raised to power 10x into 10 minus y. So that means we have y equals 10c1 e raised to power 10x, then minus y c1 e raised to power 10x. So we can put the y's together because we're looking for y. So we have y plus y c1 e raised to power 10x equals 10 c1 e raised to power 10x. So you have y here into 1 plus c1, okay, e raised to power 10x equals 10 c1 e raised to power 10x, okay? So that y alone is going to be 10 c1 e raised to power 10x all over 1 plus c1 e raised to power 10x. So this is the expression you're looking for. So you can graph this. This is a family of solutions, and the family is going to depend on the value of c1 basically. So this is like a y of x now. So you may have to resolve into partial fractions before you are able to integrate. So with that, for the rest of the questions, please feel free to um, give me your answers in the comment section. This kind of thing I did now, you need it for question 6. Yeah, you need the same thing for question 6 for sure. So partial fractions. So you need that. So let me see your answers in the comment section. Let me also see in the comment section how helpful these videos are for you. Let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And if you have not subscribed, be sure to subscribe because there's a lot more coming your way as far as differential equations are concerned. In fact, there are many things on the channel already you can benefit from in every area of math, probability, statistics, calculus, network theory, graph theory, and the rest of them. Then, of course, you want to like and share so that more people can have access to this great content. Okay. Till I come your way again, keep doing math right. Bye.